All right, so on 51 or 50 and 51, we are going to solve a system, but it's not of two linear equations. It's one linear equation, which I have already graphed on both of these, which have now disappeared. Come on back. I have been having a time with this. Okay, just maybe. We'll leave it right there. Negative 4x plus 2. That is, that's the line that I've graphed on both of these graphs because we're just trying to introduce some different types of functions and see where they intersect another function, even though they're not quite as simplistic as some of the functions we've worked with in the past. So what we want to do is we want to graph both of these other functions. And I know that when x is 0, for example, that this function will equal 2. And that as I go forward, that number will be cut into thirds. Oh, come on. Ooh. So it starts there. When x is 1, that becomes 2/3. When x is 2, that becomes 2/9. So it gets a lot smaller, but it's going to flatten out like this. And as we go backwards, it would go to the negative 1, that would be 6, and then 18. It's going to look like this. And so the point where those two things intersect is at the point 0, 2. I did want to show you these things when they're graphed. So if you hit y equals on your calculator, you can type in both of those functions and hit graph, and it should look a lot like ours. And if you hit second and trace, you can go to number 5, which is an intersect, and hit enter 3 times, and it will tell you exactly what we just looked at, that the intersection point is 0, 2. But if you look at our graph and you look at this graph, it looks like there might be another one. So we hit second trace, go to intersect again. This time I'm going to move the cursor a little bit up this direction to see if there's another one. And there is another one at -1, 6. So there's a solution at 0, 2, but also -1, 6. Yeah, right there. If my lines were straighter, then we would have seen that on our graph. But that's why I would throw that thing in the calculator, see if I can find that place where those multiple places where they meet, if they're there. All right, the next one, let's just go ahead and jump straight to the calculator since we got it pulled up. Instead of that exponential function, we're going to do this square root function, x minus 2. Is that it? Okay, so that one's going to start over here, 2, 0. It's going to go up here. And it's going to go up here, I think. You see the blue line over here. You see this line right here. If I hit second trace 5 and ask it to find me an intersection. Oh. There's the cursor. It says no sign change. That means they don't intersect in that part of the window. And in fact, they actually don't intersect anywhere. So there's no solution to this system because they never intersect. Those two functions are never equal. Continuing with some graphs, these are not systems, but these are some quadratics that we're going to try to write some solutions for. We'll just do 54 and 55 if they will load here. Yeah. So the first step, the first thing you want to do is find the vertex because we want to write these in vertex form. It's the perfect form for your quadratics once you've graphed them. We can multiply these things out. We could put them in standard form, but vertex form is great to take off of a graph and write a function. So we first just want to label the vertex. This is the minimum point, and it is at 3, -7. And that is the horizontal shift is right 3. The horizontal shift goes with the x because the x is the horizontal direction. And if you remember, you see your x, you go the opposite direction. So because this is a +3, we're going to put -3. That's how you get that shift to the right. And then the last number, the number at the end, is the downward shift of 7. But we still don't quite know what should go next to the parentheses. Is there a stretch? Is there not a stretch? Yes, there is a stretch because quadratics follow this pattern of 1, 4, 9. So as you move away from the vertex, typically, if it was just a y = x squared or x squared + 4, as long as there's no stretch, it would go over 1, up 1. If you moved away from the vertex 2 spots, you would go up 4. But we can see that that's not what's happening here. It looks like we're not going up as much. So it's maybe a half, but if we want to be really sure of that, then we need to pick a point that's on this curve. There's one here. I think there's an easier one right there. So here's another point that's on our curve. And if this equation is supposed to give all the points that are on our curve, it should give us this point, -1, 1. That is an x value and a y value. So what we're going to do is we're going to take our equation that we've written so far, and we're going to plug in the y value of 1. It's equal to a, which is some stretch factor, times the x value that we got is -1 - 3 squared -7. 1 equals, so this is -4. -4 squared is 16a - 7. We add 7 to both sides. We get 8 equals 16a. Divide by 16, and we get a equals 1/2. So that's what goes in here, and it finishes or solves the rest of the, it gives us the rest of the function. If you were to take that then and then graph it in your calculator, you should get that same quadratic that we see on the page here. All right, let's do one more. Number 55 has something a little bit different because you may notice as you look at it that there is no horizontal shift. There's no left or right shift. So in the equation, y equals some number that we're not sure about yet times x. Remember, the number that goes with the x is the horizontal shift, and there's not one. So we're not going to put a number in there because the vertex is right here. It is at 0, -4. There's no left or right shift, but there is a shift down of 4. So that's -4 at the end. And then at the beginning, if we want to know that point, we need to find ourselves another point that's on this curve. There's one right here. There's also one right here. I'm going to use the one that has a +3 comma, -1. So the x value is 3, the y value is -1. That means -1 is equal to a, some stretch factor, times 3 squared minus 4. I'm going to add 4 to both sides. I get 3 is equal to a times 3 squared is 9. Then I'm going to divide by 9. I get that a is equal to 1/3, which is what that fraction simplifies to. Let's go ahead and continue the graphing saga here. On 56 and 57, we're supposed to find the vertex, which for a quadratic is its maximum or minimum value. If it's a happy quadratic like this, then the vertex is that lowest point. If it's a sad quadratic, that means it has a negative leading coefficient, then it's going to be opening downward like that, and the vertex will be a maximum point. Okay, so we want to first identify the vertex. So the vertex on this has to do with this 5 and this 1, h and k. So remember, if you see your x, you go the opposite direction. So that one's not going to go to +5, it's going to go to -5. And k is 1. So the vertex is at -5, 1. It's right there. So that is it the minimum value or the maximum value? Well, we look here to the 1/4. Because it's a positive 1/4, that means it's going to open upward. And so this quadratic opens like this, so that we're dealing with a minimum value. Minimum. All right. We're supposed to graph the rest of it. So when given this, we have a quadratic. Quadratics follow this pattern, the 1, 4, 9. They just follow perfect squares. As you move away from the vertex, it should go up 1. If you move away from the vertex 2 spots, it should go up 4, and so on and so forth, 9, 16. But this one doesn't go up the full amount because it has an a value of 1/4. So whenever you write down your 1, 4, 9 pattern, we need to multiply all of these by 1/4. And that gets us 1/4, 1, 2.25. We did another one, it would get us 4. So as we move away from the vertex, instead of going 1, 4, 9, 16, we are going to go over 1, up 1/4. So not very far at all. If we move away from the vertex 2 spots to the left or the right, we'll go up 1 full spot. If we move away from the vertex 3, we'll go up 1, 2.25. Right there. And I can't do it on the left side, but I can do it on the right side. I'll go over 1, 2, 3, 4 spots. I'll go up 1, 2, 3, 4. And so our quadratic looks something like that. X squared minus 2. I already drew the vertex, so I'll go ahead and draw it. There is no stretch factor, no a, just a 1 up here. It doesn't move left or right. So as we move away from the vertex, it does follow the 1, 4, and if you move away 3, it should go up 9. It follows that pattern. So the one over here, number 57, is actually your typical quadratic. Without a stretching factor, it's only been shifted down 2 units, very close to the parent function. And the graphing saga continues. Whoop, a little far. All right, we're supposed to sketch the graph of this function. We're supposed to know what the minimum and maximum value of the function is, and supposed to say the y-intercept. So these are all written in standard form. And in standard form, the constant term is the y-intercept. So the y-intercept on this one is 0, 7. It's where it crosses the y-axis. And so we can't even see it on this graph. But it also asks us for the minimum / maximum value. Well, this quadratic has a positive leading coefficient. So the vertex is going to be a minimum value on this one. It has a minimum, but we have to know what the vertex is to know what that minimum value is going to be. There's a couple ways to know the vertex, but the main one that we've talked about, or the main thing that we've used, is completing the square. So that's what we're going to do. We're going to rewrite this. We're going to practice completing the square and use this to practice that skill. So if you want to complete the square, you need this thing to be set equal to 0. You're going to have x squared minus 6x plus 7 equals 0. To complete the square, so we're recognizing this quadratic isn't a perfect square. We're going to move the 7 to the other side, and we're going to leave a little bit of space, because we're going to have to add a number to the left side to complete the square. Like if you have 15 cubes and you're trying to make a little square out of those tiles, you're going to need one more square to complete that, one more little cube to complete that perfect square. We're going to do the same thing. The reason we want to do this is so that we can factor it into two factors that are the same. So like the square root of 16 is 4 times 4. We want to do the square root of this quadratic so that we have those same two numbers and we can write squared beside it, because that will allow us to solve this thing. So the way we write this in the parentheses is you just take half of the middle number. So half of the middle number is -3. And what I want you to notice is that -3, you see it right next to that 2, it's being squared. So the -3 that we added in there is going to be squared, and -3 squared is 9. So in the completing of the square, we are adding a 9 to the left side of our equation. So look at the middle number, -6, cut it in half. That's what goes in the parentheses. Square it, and that's what goes up here. And if we add 9 on this side of the equation, we have to add 9 over here as well because of equality. -7 plus 9 is 2. And so at this point, if we wanted to, I'm going to jump to the other side of the graph. If I move that 2 over to the left side of the equal sign, then hopefully you'll recognize that what I have again is vertex form. X minus 3 is a shift to the right of 3, and then -2, shift down 2, and that is my vertex. And there's no stretch on it. There was no, the leading coefficient's just 1 up here. So as I move away from the vertex 1 space, left and right, I should move up 1. As I move away from the vertex 2 spaces, I should move up 1, 2, 3, 4. And that's all I've got space for. So there's my function. And what is the minimum value of my function? It's that 0.3, -2. Let me scroll down real quick. See if there's another one of these things we need to do. Yup. Number 61 looks like something we should try to tackle. Ooh, I'm a little far. This will be the last one on this video. Jump into some discriminant talk. Okay, so number 61 is a little more difficult because it has a leading coefficient of 2 if you want to complete the square. So we're going to do it that way. We're going to complete the square. and identify the y-intercept by that last number. That's the y-intercept. It is at 0, 21. So it's another one that we don't see on the graph. It's way up here at the top. Okay, so how do we complete the square with this one? Well, if you want to complete the square, you get that constant term to the other side. So we'd subtract 21 from both sides. But you also can't have a leading coefficient that isn't 1. So what we're going to do first, after moving that 21 over, is we are going to divide all these coefficients by 2. In the spirit of Christmas, we will use red and green. So that gives us x squared minus 6x equals negative 21 over 2. Just a little bit of a fraction. It's okay, nothing to worry about. And now we're going to complete the square. It always follows this pattern. You have some number in parentheses next to an x, and that number is just half of the middle number. So half of negative 6 is negative 3. If you square negative 3, you get 9, a positive 9. So we have to add 9 to both sides. So x minus 3 squared is equal to, if you add this, you'll get negative 3 over 2. I'm going to jump back across the graph again this time. Whoops, I went to the wrong side. I'm going to jump across the graph to this side. I'm going to move the 3 halves over to the right, equal to 0. Okay, so the thing is, we divided all of this by 2 when we got started writing our equation. And so now that we have completed the square, we're going to multiply that 2 back in, very similar to what we do with factors when we use the bottoms up method. So this is going to become 2 times x minus 3 squared. We can't multiply that 2 in because in the order of operations, exponents come first. So we have to square x minus 3 before we can multiply it by 2. So we just leave it like that. But with adding 3 halves, we can multiply that by 2. So 2 times 3 halves gets us 3, equal to 0. All right, so now we've got our vertex again, 3, 3. Vertex is right there. So again, this is a happy quadratic because it opens upward. It has a positive leading coefficient of 2. So this is a minimum value that we're dealing with, an absolute minimum, and it is at 3, 3. That's the minimum value. Okay, so from there, we're going to follow that pattern 1, 4, 9, 16. But because we have a stretch of 2, an a value of 2, we have to double all of those. So that gets us 2, 8. I'm not even going to write 18 because we just don't have room for that. So we move away from the vertex 1 spot. Now we'll go up 2. Goes up twice as fast as it goes away from the vertex. As we move away 2 spots, we'll go up 8. Up 8. And there is our happy quadratic. All right, so there's a lot of graphing. We will move on to other quadratic things in the next video.